week this week. I'm thinking of showing up on Friday and maybe actually starting to do we'll either do more problems of what we've been doing now, or maybe we want to go back and start talking about some of the stuff that's going to be on the final exam, because it's not really that far off. And so I'm thinking of just kind of hanging out on Fridays for the last 2 or 3 Fridays just to do some sort of recap, not really any new material type of thing. Just because I think it'll benefit everybody. But where we left off last time, and what I really want to do today, is just a whole bunch more of these optimization problems. So you're going to have to put up with word problem after word problem after word problem. This will be our second and kind of last day of real word problem stuff. And then I think on Wednesday, I'm either going to go back and catch the first section of chapter 4, which is the hardest section of the whole chapter, and I'm kind of thinking I may do that just to get that last hard section out of the way. And then we have a couple of pretty easy sections left in the course to do. And so if I do the hard one, so I'm not doing it at the very, 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 very end, I think that'll make sense for us. And so I'll probably, like I said, I'll probably go back on Wednesday, do a little 4-1 work, and probably, I won't want to say probably, I would expect we'll have to be working on some of that on Monday as well. And then we have that couple of class times left where we'll be able to do the other 2 topics. One's really quick. I could actually show you that topic in, probably 10 minutes, and you'd be really good with it. The other one is the last topic, and I just kind of talk about whatever I can with it to get you prepared if you go on to Calc 2. So what I'm going to talk about, though, today is a bunch of word problems again that deal with this optimization stuff. And so I'm going to pull out my blank paper, because, again, I don't normally do a lot of this, but I will go a little bit more slowly if I actually have to write the stuff down. If I rattle through it, you'll zone out. I know you will. So I have some more optimization problems, and we're going to be doing a group of them here that are still pretty geometric in nature. So here, let me write the problem out, and we'll kind of go from there. And so what I want to do is I want to find the dimensions of a box with a square base if the sum of its height and width, helps if I spell, width, is 16 inches. Fairly straightforward kind of question. Hopefully it looks a lot like what we talked about last class. I will, we'll tell you the calculus, the algebra is about the same, but I wanted to do one of these box questions, and that'll kind of warm us up, and then we'll get into one where the calculus is a slightly different. Okay, so I want to find the dimensions of a box, and I guess I need to say one more thing about the box, maximum volume. Forgot that part of the sentence. For the maximum volume, square base if the sum of its height and width is 16 inches. So as I look at this, remember from last class, for the most part we're really talking about trying to find 2 equations. One of them is the thing we want to maximize, and that's what we call the objective. And one is the constraint, which is the one that typically involves a number that we solve to be able to get the objective in one variable. So what I have here is I have a box with a square base. So worst case scenario, if you don't have a clue what else to do, try to draw yourself a pretty picture. What we know is we have a square base. So if I have a square base, maybe that's going to tell me that those two dimensions are the same, so I'll call them x and x. And then because it's a box, we have a third dimension. We'll call it y. Now, I need to maximize the volume. That's what the question is asking me to do. So I probably need that volume formula. What's going to be the volume of that particular box? XXY, I hear. X squared Y, XXY. All right, because remember the volume is length times width times height of a box. This is the one I want to take the derivative of, but I have 2 letters of the alphabet. I need to get rid of 1. And so I come to the rest of the information they gave us. The sum of the height and the width is 16 inches. So the height is my Y. The width is one of my X's. Gives me 16 inches. Then what did we do last class?
Solve for one.
Yeah, solve for one of those. And I think Ryan's already suggesting we solve for Y, and I'd probably agree with Ryan. If you actually solve this for X, you have a little more algebra to do. This is one that's actually, the problem will be a whole lot easier if you just solve this one for Y. So Y is 16 minus X. And then once we solve for Y, we take that and we put it back into the objective equation. Again, this was my objective. This one's the constraint. That's the one we always take the derivative of. So when I put that back in, V is x squared times 16 minus x. If I'm so inclined, I could actually take the derivative of that using the product rule. I am not quite so inclined to do that. I'm inclined, just like I did last class, to try to do some algebra and get rid of those parentheses, make my life a little bit simpler. And so if I do that, that gives me 16x squared minus x cubed. Now I've done absolutely no calculus. Now I get to do the calculus. So what do I need to do the calculus? Find the derivative. Just on this lovely Monday morning, what's the derivative going to be? Yep. 32x minus 3x squared. Then what do I do once I find the derivative? You got it. This one, notice I've got a step here. Both of these have x's, so I can take out the x. And when I solve this, I end up getting either x is 0 or x is 32/3. This is that situation I mentioned last class where sometimes we get 2 answers. One of them either gives us the wrong thing or it makes no sense. Probably it's pretty obvious to you that the 0 makes no sense in the problem. If we're going to maximize the volume, you certainly do not want one of the sides to be 0. Wouldn't be much of a box. So I'm anticipating the 0 has nothing to do with the problem. I am going to put it on my number line though, just to make sure I pick numbers in the right places. And so remember, I need to double check. I'm guessing this is probably the answer, right? But I need to double check, so I picked my favorite numbers for test points. I am actually going to pick something smaller than 0. Let's see, 32/3 is 10 2/3, so let's pick 20 because we know that's bigger. And remember, I plug those into v prime or whatever the derivative is. So if I put -1 into the derivative, that's going to give me a negative. You can check it. So do v prime at -1. Do v prime at 1, gives me a positive. And v prime at 20, I'd have to do a little math out there, but I'm going to do it this way because this will make, I'm going to use the factored version. 20 and 32 minus 3 times 20. Yeah, that's going to be the negative that I expect it to give me. So notice that would give me the minimum, because I go from decreasing to increasing. The 32/3 gives me the maximum. So let's go back to the question. Find the dimensions of the box. So I know that my x is 32/3. All I need is the y to get the third dimension. And so I know y is 16 minus x. So y is going to be 16 minus 32/3. If I do that, that gives me 16/3. Gives us a point that I haven't actually brought up before. But if we actually have, typically if we have a box, if we have a rectangle, that, if we have those types of shapes, if every side has the same weight, so we don't have the situation where one side is twice the other, if we actually have everything being the same, everything being equal, that typically rectangles have areas that are optimized as squares, and boxes would be cubes. Now, don't think that every single problem will give you that, because again, if I use some language that says something like, the length is 3 times the width, then you're not going to have that box situation. We'll actually have a 1/3 or a 1/4 situation going on. But don't be surprised in some of them if you're like, oh, that's a square. Because if you have fencing and you're going to fence in an area, as long as the fencing has exactly the same weight, same price, same whatever all the way around, your maximum area is always going to be a square. So that was kind of a good question, because it just kind of woke us up to exactly the same process that we did last time. Let's do one that's almost the same process, but is going to have a little different calculus, because I want to make sure I show you kind of the second version of calculus that will happen. And then I've got a couple of other geometric questions that are a little bit tougher that I want to make sure I do. So what I'm going to have here is I'm going to have a field. So suppose we say a field is enclosed by constructing a fence costing $4 per linear foot on 2 parallel sides, and a stone wall costing $5 per linear foot on the other 2 sides. So what I want to do is I want to find the dimensions that minimize the cost if the area enclosed is to be 1,000 square feet. So we're going to enclose a field. It's going to be a nice little rectangular field. And it's going to be enclosed by constructing a fence costing $4 per linear foot on 2 parallel sides, and a stone wall costing $5 per linear foot on the other 2 sides. Find the dimensions that minimize the cost if the area enclosed is to be 1,000 feet. Hopefully we've done enough of these that you can see at least a description. Doesn't mean the equation, but that you can see a description of the 2 equations we need, the objective and the constraint. Notice, minimize the cost. So the cost is going to be one of our equations. And we know the area is 1,000 square feet. So again, Hopefully we're at the point where that's making sense to you, that you're like, okay, I see, I'm able to pull that information out of the question. So again, I told you this is going to be rectangular. So there's my rectangle. Again, even though I have some cost things going on, I still have the dimensions. And so maybe what I'll do is, I'm going to use L's and W's. Maybe there's an L, there's a W. The nice part is it doesn't really matter where I call the $4 sides and the $5 sides, as long as I make them parallel. So maybe these are the two $4 sides. That's another L. Right, $4 per foot, $4 per foot. And then maybe this is $5 per foot, $5 per foot. So there's kind of a picture. I always recommend draw a picture first. One of the equations is pretty easy to get. It's the area. And remember, to get area, the cost doesn't matter to us. So the area of any old rectangle is base times height. So we know the length times the width is 1,000. That's the easier of the two equations. Don't put the cost in. The cost has nothing to do with the area. The cost has just to do with the cost of the cost equation. So my other equation is going to be cost. And I'll ask this question. How are we going to figure out what the cost is? How are we going to write that cost equation? It's related to the perimeter, yeah. Is it just the perimeter? Is it just 2L plus 2W?
4 plus 2W times 5.
Ryan tells me 2L times 4.
8W, or 8L.
So that's okay. I'm going to write it this the way you said it for right now. Plus 2W times 5. I actually like the way you kind of said that. A lot of people would actually do it just even slightly different. They might say, okay, it's L times 4 plus W times 5 plus L times 4 plus W times 5. You know, the cost for each side, and we add them all up. Right? If we are on the fence side, and we put in 1 foot of fence, it's going to cost us $4. If we put in 2 feet of fence, it's going to cost us $8. If we put in 3 feet of fence, it's going to cost us $12. If we put in L feet of fence, it's going to cost us $4L. And so to do the cost, it really just becomes the length of the side, length or width of the side, however you want to put it, multiplied by the cost for that per foot for that side. And so Ryan correctly said we could actually just call this 8L plus 10W, and there's our objective equation. Ooh, hope the roof doesn't blow off. Wow, I can really hear it rumbling through here today. Ryan and I are like, okay. Oh. That's quite a noise, isn't it? I've never heard that in here. It sounds like thunder. It actually sounds like we have thunder, but I know it's just the wind blowing against the building. So we have no windows, so at least we can't see what's blowing by like Dorothy and Toto or something here. So those are our two equations, though. And again, objective and constraint, the one we want to take the derivative of, the one we want to minimize is our objective. Right? We're going to need C prime. But again, we don't want 2 letters, we only want 1. So we go back to the other equation and we need to solve for one of the 2 letters. You know, before last class I said, oh, pick the nicer one, pick the easier one, pick what you want. This case, it's not going to matter. It's virtually identical either way. Might be a little less, the numbers might be a little less funky if I solve for W. But it's not really going to matter. No. W would be 1,000 over L, and then remember we put that in the C equation. So C is 8L plus 10 times 1,000 over L, 8L plus 10,000 over L, and that's our C. Why did I want to do this one? Well, I want to do this one because my next step's the derivative, and you'll notice I don't have a polynomial this time. I'm going to recommend, if you have a problem like this, that you don't use the quotient rule. I'm going to recommend, before you take the derivative, that you just bring that L up and make it L to the -1. It'll save you a little bit of pencil lead if you don't have to use the quotient rule. So bring that denominator up, change the exponent, right? The exponent would be 1, comes up as -1. And now I can take the derivative. Gives me 8. And I'll put the plus in, even though I think it's going to be a minus by the time I get done. Now I just take the derivative. Remember, the 10,000 is along for the ride. -1 comes down in front. -10,000, L to the -2. Which I'm just going to rewrite as 8 minus 10,000, and I'm going to drop that back to the denominator. Actually, it'll make your life a little less challenging. Now, this is kind of an interesting situation. Remember when we just did the last problem, I said, oh, what do we do? And you said set it equal to 0, and that is true. But also notice, this derivative actually has a place where it's undefined. So not only do we want to set it equal to 0, but we also want to notice that it's undefined at L equals 0. That's going to give us, a second or third value to worry about. Again, does the 0 really make any sense in the problem? Do we really want to have a length of 0? No, it wouldn't be much of an enclosure, would it? So I'm going to take this second piece, though, and set it equal to 0. If I do that, probably the easiest way, quite honestly, is to move that to the other side and do a little cross multiply. So 8L squared is 10,000, which means L squared is 10,000 divided by 8. Right, and we can do a little bit of math. So if I got it right there, that's going to give me 1,250 if I did the math correctly. And so L, again, technically is plus or minus the square root of that, which is about 35.4 if my math is correct. Probably should put my about symbols and not my equal to symbols. And again, you might go, the minus makes no sense, lady. We're talking about sides of a rectangle. Well, for the process, we want it just so that we put our pluses and minuses in the right place. So now I'm going to make my sign bar. I've got minus 35.4, I've got the 0, and I've got the 35.4. How about putting it on the screen for you? And then what I would typically then do is pick some numbers. So I'll pick maybe L is -40, L's -1, L's 1, L's 40. Plug those into the derivative. Think what you're going to find. Those two actually give you the same value when you plug in -40 and 40, and they'll both give you pluses. If you plug in -1 into the derivative, you're going to get a negative. If you plug in +1, you're going to get a negative. Even though it makes no sense mathematically, this gives us a maximum. This gives us nothing. Actually, there's a flat spot in the graph. And this one gives us the minimum that we're looking for. Which we probably, just from the numbers we had, we could guess that that's the one that's supposed to be the minimum. But it's nice to double check that. Now I go back to the question. And again, it said find the dimensions, so I have my L. So I need my W. So I know L is approximately 35.4 feet, and W will be 1,000 divided by 35.4. Which is about 27.5, if my math's correct. Bless you.
Thank you.
This was not all that different from the other questions we did. It had just a little bit of different algebra, and I wanted to just show you that algebra because that does happen fairly often. That bring the power up and do the derivative and go from there. We are a healthy group. Glad most of you haven't been around me. You can't blame me for it. How am I doing? Good, I'm doing fine. I have another algebraic question, and on this next one, I'm going to warn you, I'm going to set the problem up. I don't think I'm going to do the calculus part. You'll actually, when you have them, you'll actually have all of the work done out. But it's not really the calculus that's going to give most of you trouble. It's going to be the setting it up. So this one's kind of an interesting question. It's a little bit different. And then the one I'm going to do after this is the hardest question in the whole group, the hardest of every single optimization question. So this one's a little bit of a warm-up to it. It's a little bit different. The next one's the hardest one, and it's more because of the calculus. And that is one I'll do the calculus on. So what we have here is I'm going to have a sign. And the sign is to contain 50 square inches of printed material with 4-inch margins, top and bottom, and 2-inch margins on each side. And what I want to know is what dimensions minimize the amount of paper, let me a paper sign, used. So, sign is to contain 50 square inches of printed material with 4-inch margins on the top and bottom and 2-inch margins on each side. What dimensions will minimize the amount of paper used? And what I'm really going to be doing, I'm going to write this in here, I'm going to be minimizing the area. That's really what my goal is going to be. It'll give me the dimensions. So I'm going to minimize the area of the entire sign. So what we're going to do is here's my piece of paper. Let's see if I can get this so it looks a little bit to scale. So there's supposed to be the paper piece. I'm going to do this the way that when you see it in online in the notes, when you get the paper notes, that it's going to be consistent. There's 2 ways to set it up. I don't really want to do it one way and have you look in the notes and see something else. So what I'm going to do is, because I know this is know something about this part, I'm going to call the printed dimensions X and Y. And then I know this is for this is 2, this is 2. It'll make my math a whole lot easier to do that, to call what I know the x and the y. So one of the equations is x times y equals 50, because that's the 50 square inches of printed material. Which equation is that going to be, my objective or my constraint? That's the constraint, because that's the one that's got the number in it, isn't it? That's not the one I want to take the derivative of. What I want to take the derivative of is the whole sheet of paper. And so I'm going to call that P for paper, not P for perimeter. I'll do that. The rest of the word paper in parentheses for a moment. And now when I go to do that, I'm going to get the area of that, which means I'm going to have x plus, yep, and y plus 8. And that's the area of the big piece of paper. That's what I want to take the derivative of. Again, I got this variable issue. I've got 2 of them roaming around. So just like I did in the previous question, that's why I'm not going to do the calculus when I get to it, I'm going to have the situation where I'm going to have this denominator going. So I think I'm going to solve for y. I think most of you would probably prefer I solve for y. Again, it doesn't really matter here. But y is 50 over x. Put that into the equation. And that's what I want to take the derivative of. Again, I could use the product rule, but again, I'm not going to. I'm really trying to get you to notice that when possible, don't use the product rule, multiply it out. And so if I do that, firsts are going to give me x times 50 over x, just 50, you got it. Outers are going to give me 8x. Inners are going to give me 4 times 50 over x, which is 200 over x. And the lasts are going to give me 32. So neatening things up a little bit. 82 plus 8x plus, and I'm going to do a little step here at the same time, 200 x to the negative 1. I'm going to go one more step, and then I'm going to say the algebra works almost identical to the previous question. So we would take the derivative. What's the derivative of 82? 0. Yep. Plus 8x, and the derivative of that's 8. And then here I'm going to have minus 200 x to the negative 2. Again, we have that undefined at x equals 0. And again, I'm cheating, we're going to have plus or minus some number. And again, you're going to make a sign bar. And notice we're minimizing. You actually end up with exactly the same sign bar we had before. And again, you'll get the number and you'll find the other side. Hopefully the calculus or the algebra really there, you're like, okay, yeah, give me a couple minutes and I can do that. Actually, I think you had a nice number on that one. The only thing I have to be careful about here is this is going to give you x. It's actually asking you the dimensions of the paper. And so in order to get your final answer, you'll need to add 4 to the x that you find, and you'll need to add 8 to the y that you find. So, because when you get just x and y, you're not getting the paper, you're getting the print. Does that make sense? Now, are you ready to do the hardest question in the whole group? No, but we'll let you do it to us, lady. This question was actually, and I'm doing a different one than I used to do. But this question was one that there's actually been a whole lot of research and things written on it. In fact, it was interesting, it was way back, probably 15, 20 years ago. I was getting ready to do this topic, and I used to belong to an organization where I would get a mathematical journal once every couple of months. And the guy had written about how he had actually done this problem out experimentally with his dog. And now, here's the dog issue. Here's the dog problem, and we're not going to do the dog problem. We're going to do a little different one. What the guy wanted to do was he was on the beach, and he wanted to figure out kind of where his dog or how his dog would run to get a frisbee into the water. And he wanted to run this test where he could figure out, does the dog take the best angled route to get there? And what does the calculus say? Now, does the dog really know kind of what it's doing? And so he ran it mathematically. He actually would time the dog and do measurements of what the dog was doing. The poor dog was probably exhausted by the time. And he actually found that the process that the dog was using to get to the frisbee, because the dog wasn't just running out into the water, the dog actually was running down the beach and then going in the water. That it was really bizarre, but the dog was taking the path that actually the calculus says you should be taking. And so it's just kind of weird, because you wouldn't think the dogs wouldn't be doing anything like that, but it was something naturally inherent in the dog that was causing it to do this. So I'm going to do a little different problem. I don't have the dog going. But what I have here is I have a situation where what I have is I have a situation where a guy is out in his rowboat. So here's the situation. Out in his rowboat, rowing along, out floating out in the water. And he looks on land and he sees his house burning down. He wants to get to his house as fast as he possibly can. Right? We know that you probably could imagine that you row at a different speed than you might actually run to the house. And so the question is, do you head right to land and then run, or do you head at an angle to the land and then run? And so that's the situation. So let me write it out in words so you kind of know where I'm going. So what we have is we have Anton. And Anton, who is in a rowboat, is 2 miles from point B on a straight shoreline. I'm going to leave some space. I'm going to start to draw the picture. So here's the shore.
They can't see that.
Oh, they can't see that? I can't see anything. Let me get that back up. I pressed the button and it didn't take it. There we go. So Anton, who's in a rowboat, is 2 miles from point B on a straight shoreline. So there's the shore. There's point B. And there's Anton. I use a name that begins with an A. So I have point A and then point B. And what I know is that distance is 2. And so what happens is he notices smoke coming from his house. Which is 6 miles. How he knows these distances, I don't know, but 6 miles from point B down the shore. So here's his house. That's 6. he can row 6 miles per hour and run 10 miles per hour. And what we want to know is, how should he proceed to get to his house in the shortest time? We know what the shortest distance would be, but because he rows slower than he runs, we probably want to get him to land someplace in between. And so if you can imagine the dog situation, the dog can run faster on land than he can swim in the water. And so we want him to run a certain distance and then swim, but it's not a perfect 90-degree angle that's going to make it work for us. So what's going to actually happen is somehow Anton is going to get to here and then go down to there, someplace in between. This is an equation that has basically that modified objective constraint thing going. So what's happening is, though, I want to get the shortest amount of time, so that's going to be my objective equation, is to do something that's going to get us the shortest amount of time. So the way I'm going to set this up is I'm going to pick a dimension. I'm going to pick one that makes the most sense for these types of problems. I'm going to call, I could do it either way, but I'm going to call this dimension from here to here x. And notice that now gives me this lovely little right triangle. And so this dimension here is the square root of x squared plus 4 because it's a lovely little right triangle. So if I happen to call this d, what that tells me now is, and if I look at the picture, I know one side is 2, the other is x. So x squared plus 2 squared is d squared. That's really what I've got going there. And then this distance, if this part is x and the whole thing is 6, this distance has to be 6 minus x. And I've labeled like every single dimension in the whole picture. Now again, I need something for time, and I have written down nothing that has to do with time. What comes into play is the fact I know his speed, I have some expression for distance, and I actually remember from days gone by that rate times time equals distance. Or in other words, time is distance over rate. And I now have an expression for his distance in each case, and I know his rate in each case. Right? This is never a problem you could probably ever come up with on your own. And so now what I have is, I can get his time rowing, which is going to be his distance rowing, divided by his rate rowing, which we said is 6, and I just converted that radical into a fractional exponent because I know I have to take the derivative. And his time running is going to be 6 minus x divided by the rate he can run. And his time is going to be the sum of those two. There's the equation that we're going to take the derivative of. Usually once you see one or two of these, you're like, okay, they all work the same. If you want to minimize the time on a problem, they all work exactly the same. Maybe you don't have as much, you may not have the right triangle, but most of the time you do. Most of the time you have this x and some number minus x. They're pretty much the same question, but you do have to see it a time or two. This is what I now want to take the derivative of. And I'm going to tell you, your life is going to be a whole lot easier if you think of the 6 and the 10 as 1/6 and 1/10 out in front. And in particular, before I ever take the derivative, if you distribute that 1/10 through, your life will be a lot more exciting for you. Notice I cannot, and please, I cannot put that 1/6 inside of that parentheses. That exponent forces us to not do that. It's not legal. Bad algebra. We don't want any bad algebra going on. So now I can take the derivative. In order to take the derivative here, the 1/6 is along for the ride, and I need to take the derivative of what I put in the box. And to take the derivative of what I put in the box, I need to use the chain rule. You got it. Derivative of the outside, 1/2. Keep the inside the same, raise to the negative 1/2. You got it, times 2x. Derivative of the outside, derivative of the inside, keep the inside the same once I do the derivative of the outside. And then here, this is fairly easy. 6/10, derivative is 0. 1/10 x is just 1/10. Clean up this non-exponential piece of it. And if I do that, that's going to give me 1/6 x squared plus 4 to the negative 1/2. And then minus 1/10. Just rearranged the stuff and brought everything other than the parentheses up front. Set it equal to 0. I'm going to do some fancy dancing rewriting here. This is actually going to be the same as x over 6 times x squared plus 4 to the 1/2. So I just dropped that to the bottom. The 6 is in the bottom, the x is in the top. And at the same time, I'm going to move the 1/10 to the other side. The reason that's helpful is I can now cross multiply. Multiply by the common denominator. Gives me 10x equals 6 times x squared plus 4 to the 1/2. The 1/2 power, remember, is the square root. And so the algebra I want to do here is I want to actually square both sides. It's an equation as it's written, so I can square both sides. Just for your notes, I'm going to write it as a second. And if I do that, that gives me 100 x squared equals, don't forget to square the 6, that gives me 36. And then just plain old x squared plus 4, because the square root and the square would cancel out. So each factor there gets squared.
Can you just square root the x squared plus 4?
You can't just take the square root of the first and the second. Remember, that's not a legal step to do.
Like, if you rewrote it 6 square root x squared plus 4, and then take the square root of that, and then multiply the 6 through? Because, I guess.
You can't, that algebra, you can't take the square root separately. Yeah, I can't write this. What Ryan's asking, I think, is can we do something with this? And the problem is, there's not a whole lot of simplifying we can do. If I want to bring the 6 inside, it actually goes in as 36. But then I still have to square both sides to get rid of it. I can't take the square root of each piece. It's just not going to give me the same thing. So now in any event, I have 1000x squared equals, I'm going to rattle through the algebra, 36x squared plus 144. Bring the 36x squared to the other side. This is rigged so it comes out nice. 64x squared is 144. X squared is 144 over 64. And you'll notice I'm not reducing that because I actually know I need to take the square root and I know those square roots. So I know I'm going to get 12 over 8. Three over 2, 1.5. Negative 1.5, positive 1.5. In the interests of time, I'm minimizing what you should find. If you pick some numbers and do the math, that you'll get plus minus plus. So what we learn is he needs to go, he needs to drop 1.5 miles below B, which means he's going to run 4.5 miles. And if I were so inclined, I could actually figure out that distance as well. Algebraically, that's the ugliest question we do. Usually I explain it slowly enough that students are like, yep, I have it. But if you go out and this afternoon, you write down that question, you try to do it, most of you will be like, well, wait a minute, what did she do? How did she do that? So it's one that you're going to want to study a little bit. Okay. What do you think? Is it time to call quits? Yep. Don't forget, I'll just remind you, web assign was put on this morning, collected assignment was put on this morning. Wednesday, we're going to, I think I'm going to talk about the hardest topic in the course. Friday, for anybody who's interested, we're just either going to go through some more optimization problems, or I'm going to talk a little bit about, we'll start talking a little bit about some of the early stuff for the final exam. We'll chat on Wednesday of what we want to do on Friday for anybody who's interested. So have a good one. Don't blow away. Hopefully we all keep power today.